Good afternoon. My name is Gerui. Welcome to the XDC session. And today I will introduce you XDC 2.0, security and scalability with sovereign EVM compatible subnet. First, I will introduce you to XDC network. Then I will show you our core protocol from XDC 1.0 to 2.0. Then I will introduce our unique and crucial service, namely forensic monitoring service. Then I will show you our scaling solution, XDC Subnet. The XDC network is an open source, carbon neutral, enterprise grade, EVM compatible layer 1 blockchain. It was the first and the only blockchain to be invited to join the Trade Finance Distribution Initiative. It is a consortium of the world's leading bank and non-bank financial institutions for the purpose of liquefying trade finance. We also call ourselves the XDC network the third generation of blockchain. So the first and the second one, they are Bitcoin and Ethereum. For the transaction per second, XDC reaches over 2,000 TPS, and the average gas fee is extremely low. The transaction confirmation is 2 seconds and with finality. Finality means there's 100% guarantee. It is not probabilistic. And for smart contract support, XDC network is yes. It has EVM-compatible smart contract support. And for energy consumption, it is very low. It is almost negligible. It is because we do not use the proof-of-work mining of Bitcoin or Ethereum. I mean the Ethereum 1.0, before the POS merge. Next, I will walk you through our core protocol from XDC 1.0 and to our upgrade 2.0. So XDC 1.0, it is a highly efficient and fast consensus protocol. It uses delegated proof-of-stake depots. This means that every node needs to stake 10 million XDC token to be a masternode candidate. And we will elect a fixed number of masternodes from the candidates. Currently, we elect 108 masternodes, and this number can be scaled up when the network grows. So it works as follows. The masternodes, they are in an order list, and they take turns to produce blocks. And when they produce block, they sign the block, and in the figure, it is denoted as M1, the first signature. To make it more secure, we have the double validation mechanism, which means that signatures from 2 masternodes is required for each block. And only with 2 signatures, the block can be accepted by the network. It works as follows. So actually, our randomly assigned second masternode, denoted as M2, needs to sign the block. And I am happy to announce that our upgrade, our consensus upgrade to XDC 2.0 consensus protocol, which is more secure and faster. It uses the state-of-the-art Byzantine fault-tolerant consensus protocol, which means it is secure even when 1/3 of the masternodes goes adversarial. It also has super fast transaction finalization, only 3 blocks for a transaction to be finalized, and the finalization is deterministic, which means 100%, and the transaction is never rolled back. And the most important service we provide by XDC 2.0 is our built-in forensic monitoring protocols. This means that attackers who wants to create a fork on the blockchain and break the consensus, they will be slashed with their stake tokens. And we have a theoretical guarantee for that. I will come to the forensic monitoring later. So how does 2.0 work? So instead of the double validation, which requires only 2 signatures, we require signatures from 2/3 of the quorum of the master nodes. So currently we have 108 master nodes, which means we need 2/3 times 108, but plus 1, which means we need 73 signatures from master nodes for each block. This increases the security level. And the 73 signatures constitute a quorum certificate, or QC, which is a crucial concept in our protocol. And the QC is carried by the next block. So the use of QC enables the XDC network to upgrade the consensus to the hot stuff consensus, which is the state-of-the-art consensus in both academia and in industry. It works as follows. So the protocol proceeds in rounds, like round 1, round 2, and so on. And again, in each round, there's one block producer who should produce the block. After this producer or proposer who produces a block, it propagates the blocks throughout the network, and other master nodes, when they receive the block, they should first validate the block. That is, check whether the block itself is valid, and then it checks whether the proposer is the correct one specified by the protocol. If these tests are passed, then the master nodes votes or sign a signature for this block, and also propagate this vote or signature throughout the network. It is the duty of the next block proposer to collect the votes from 2/3 of the master nodes, which is 73 votes, and combine these votes into a QC. So this means that the QC is piggybacked by the next block. That is, block 2 is piggyback QC for block 1, block 3 piggyback for block 2, and so on. So it's a little bit complex, but the advantage of this complex consensus protocol is that we have fast and secure finalization. Proved by the hot stuff protocol in theory, only 3 consecutive QC mean a block is finalized forever and with 100% confidence. This means that if the block interval is 2 seconds, 3 block is only 6 seconds. 6 seconds you can confirm a block, and the block is never going to be rolled back or reverted. As shown in the figure, so after the proposer send the block, all the master nodes should vote for the block, and hopefully that 2/3 quorum of these master nodes, the votes of these master nodes will be formed very quickly. Okay, next I will introduce our unique and crucial service, namely forensic monitoring service. Forensic monitoring service means that whenever any master nodes, they turn adversarial and they want to create attack to the blockchain, our service can detect the attack and can hold the attackers accountable. We have 2 very important points to ensure that. First is that by our protocol design, the attackers must send signatures to launch such an attack. And these 2 signatures is actually the evidence of this attacker. And the evidence will be collected by our service, and then the evidence will be sent to a smart contract, and the rules specified by inside this smart contract will slash the attacker's stakes, and they will lose their stake tokens. And this is a very simple example shown in this figure. That is, at the end of this blockchain, there are 2 blocks at the same height. which means there are two forking blocks. Because maybe some honest nodes or normal nodes, they are in different locations or their network conditions different, so some honest nodes sign for one block and the other honest sign for another block, but it's okay. What should be held accountable is the adversary shown in this figure, that who signs two blocks or votes for two blocks. And these attackers will leave the evidence and will be held accountable by our service. And in reality, the condition or situation is much more complex than that. Some nodes have very poor network connectivity, so they may vote for this fork block once, and then later they see another longer chain and vote for another fork block. But our service will not hold them accountable because they just suffer from poor network. But if any attacker that is on purpose trying to launch such an attack, our service is guaranteed to detect them and to slash their stake tokens. With sophisticated analysis of the hot stuff consensus protocol, and we publish our result in a top-tier academic paper. So our forensic monitoring service ensures that the attackers cannot successfully launch an attack unless they control beyond 1/3 of the master nodes, which means it's 37 nodes, 37 master nodes, and if they launch an attack, they will lose all the stake tokens of these 37 master nodes. We also ensure that attackers must leave irrefutable evidence. Irrefutable means that attackers cannot say that I am not doing badly, I am not doing adversarial. If our service has the evidence, then the attacker must misbehavior and their stakes must be slashed. We also ensure that the evidence of the attackers is guaranteed to be discovered by our service. That is, they may try to hide their evidence. They just send the message to a selected small number of other master nodes, but that will not hide their evidence. In the end, their misbehaving messages or evidence will be transmitted to our monitoring service, and they will be slashed. And finally, we ensure no honest nodes will be framed. That is, the evidence will not forcefully accuse any honest master nodes. And shown in this figure is our currently running and live forensic monitoring service on our DevNet. And you can see that we have launched several toy attacks, and our monitoring service cached them. We have the number of the blocks that is affected and how many attackers are involved in this attack, and so on. Okay, so lastly, I will introduce our scaling solution, namely the XDC subnet. So by starting a subnet, you can scale your performance. For example, for each different application, you start your subnet, and the subnet only runs one application, so it's much faster than the mainnet that runs multiple applications. But beyond that, we have other motivations, that is privacy, security, and sovereignty. So for privacy, it is that some customers, for example, some enterprise customers, they do not want the transactions on blockchain or the ledger to be disclosed to the public. And for security, is that the customer also wants to harness the security level of the mainnet, because mainnet is much more secure than the subnet. As for sovereignty, it means that the subnet should be a standalone blockchain. This means without the mainnet, the subnet should work fine with itself, and the subnet should be customizable. For XDC, it means that the parameters can be changed. For example, how much reward the master nodes get, and what are the initial number of master nodes, something like that. So the customer wants to wholly own this subnet. So we have our subnet design as follows. So our approach to ensure security is security via checkpointing. The subnet owner deploys a smart contract on the mainnet, and the subnet headers are checkpointed or uploaded to the smart contract. And in this way, we can harness the mainnet security level. I will go into more detail. And this is our detailed architecture. First, the customers can run a sovereign blockchain, and it is powered by XDC 2.0 protocol, which is highly efficient. And it is also compatible with all the XDC tools. And of course, XDC blockchain is EVM compatible, so it supports native EVM smart contract. What is more important is that the account format or the address format for subnets and the mainnet is the same, which means that you only need one private key or account to work with multiple subnets and the mainnet. This is what interoperability means. So we have this subnet here, and we have the mainnet, which we have a smart contract deployed in the mainnet. It's for the checkpointing reason. And we have the relayer, the trustless relayer, who is in charge of uploading the subnet headers to the mainnet. So the relayer listens to the subnet header and encode the header and upload them to the mainnet smart contract. The uploading is through the transaction, so the relayer has to pay the fee, but the XDC gas fee is quite low. It's not a big deal. And the relayer is trustless. This means that anyone can be a relayer, and there may be some adversarial relayer who uploads some invalid header, but it is okay because our smart contract will validate the header first and then store the valid ones and just ignore the invalid headers. And to harness the security level of both the subnet and the mainnet, we have our Wallet Plus. So a Wallet Plus is a wallet for the subnet. Just like a normal wallet, it can submit and confirm subnet transactions. What is more, it can interact with the XDC mainnet through API. It can query that whether the subnet block header is uploaded to the mainnet and whether it is finalized, what is the finalization status of it. So after confirming that transaction or the header that contains the transaction, the block that contains the transaction is finalized in the subnet and also uploaded to the mainnet, our Wallet Plus can provide extra security for transaction confirmation. So let's make a comparison to the other scaling solutions. So for Ethereum, we have many layer 2 solutions. For example, optimistic rollup, ZK rollup. I believe these two are the leading ones. And Avalanche has launched their subnet design as well. And XDC, we have our subnet too. So the Avalanche approach is that their model is that a subset of the mainnet validators will be the subnet's validators. In contrast, in XDC, any customers, any nodes can be the subnet's validators. And our model is that the subnet will be checkpointed on the mainnet. As for scalability, all the solutions are quite good. For the security level, the Ethereum layer 2 solutions, they have only the mainnet level. As far as I know that no Ethereum solutions says anything about their layer 2 security. As for the Avalanche, the security level is only the subnet level, which means that they do not resort to the security level of the mainnet. For XDC, we have both the mainnet and the subnet security level. For the security approach, the Ethereum layer 2 have fraud proof for optimistic rollup, ZK proof for ZK rollups, and for the data availability problem, they have data availability proof, and recently there is this restaking mechanism that is used for data availability proof. Avalanche requires the validators to meet certain requirements to be in subnet, such as the validator should be all located in one country, or they should have some certain level of network connectivity. For XDC, our security approach is that the mainnet keeps an immutable version of the subnet header chain in the smart contract. The smart contract will also validate the headers when they receive them. And all these solutions, they are EVM compatible, and that is good. As for interoperability, which means whether the users can use one account to interact with multiple chains. For Ethereum layer 2, it depends. It depends on whether their solution use the same account model with the Ethereum mainnet. And for Avalanche and XDC, it is good. We have interoperability. For privacy, Ethereum layer 2 solutions, it also depends. Some solutions does not disclose or upload the full transaction data to the mainnet, but some choose to upload the full data. And for Avalanche and XDC, the subnet data is kept inside the subnet. It is never uploaded to the mainnet. Only the header is. So we have privacy. As for sovereignty, Ethereum layer 2 is also depends. As far as I know, all the layer 2 solutions, they run their own layer 2 network. Maybe it's not a network, maybe it's just a single node. So there's no sovereignty in them. And for Avalanche, to be a subnet validator, you have to be the mainnet validator first. So I can say they have only partial sovereignty. As for XDC 2.0, we have a fully or wholly owned subnet, which means we have fully sovereignty. Anyone can run the subnet. And the subnet is standalone from the mainnet. Even the mainnet crashed down, which could never happen, I guess. Your subnet will continue to work. So to summarize, XDC 2.0 provides you another choice for EVM compatible or EVM based dApps. And its advantages include the state-of-the-art consensus engine, which is secure and efficient. And it has the unique and crucial forensic monitoring. Ensures that attacking nodes will be slashed, and we have theoretical guarantee for that. And our scaling solution, Subnet, it is sovereign, scalable, customizable, and interoperable. So thank you, and this is all for my talk. And welcome to follow us on Twitter and visit our dev forum, xdc.dev. Thank you.
Check. There we go. So if we have any questions for Gary, raise your hand. Yeah, Great. Speak loud, please.
Hey, the name is Alex. Thank you very much for your presentation. It's heavy tech and quite interesting.
I cannot hear.
Oh, sorry. Now
Thank you.
it should be better, though I can hear myself a bit too loud. So the question is, you said you having immature headers or any case of subnet in validator, which means that in a sense, I can produce amount of subnets and overload the cost of having validator, or how exactly the archiving and storing process happening. Otherwise, the mainnet, it seems a bit exploitable.
Sorry, can you repeat your question? I did not hear it clearly.
Apologize. I mean, you said in sense of security, validator has to have immature headers of the contract. I missed that part actually, or the checkpoint.
Yes, the mainnet smart contract that checkpoints the subnet headers.
Yes. So if someone will want to abuse your mainnet, he can create repeatedly en masse subnets, and validators has to store it. And this way, I do not know. Do you have ways to archive overload of this type? What will happen with the mainnet?
Yes, let me try to rephrase your question. In my understanding, thank you for your question. In my understanding, you are saying that what if someone tries to upload like spam or garbage data to the mainnet?
Not exactly. I mean, while you're creating subnet, creating immature header that has to be stored, and you can spam by creating of subnets that mainnet and overload it. That's my question. Can you handle it, and what exactly will happen if the case?
Yes. So firstly, the XDC network, the mainnet, its capacity or its ability to support transactions is quite high, and currently the traffic is not that high. So to push the traffic on mainnet to go beyond its capacity, I think it takes quite a lot of maybe powers to do that. And also, I think in Ethereum, it's kind of like an unavoidable problem. That is, some transactions is not useful at all, or it can run some smart contract, but it is meaningless, something like that. I think it is unavoidable in any Ethereum-compatible blockchains.
In most cases, I believe yes, but in case of Bitcoin nodes, we know already you have to have a terabyte of bytes in order to maintain it. And the process is infinite. If you have no mechanism to store it, then after 10 years, probably it will be tremendously overloaded.
Yes, but yeah, in the 10-year scale, maybe the data is large. I have not done the calculation, but I want to say that we only upload the header data, which does not include the transaction payloads. So this means the header is much smaller than the whole block data that includes payloads. And also the data, like data growing or data explosion problem, is also some problem that exists in many other blockchains. And actually, I know Ethereum has some solutions tries to solve them, such as proto-dank sharding, something like that.
I see. Thank you very much.
Thank you.
Yeah, give him a round of applause. Thank you for Gary, please.
Thank you.
Thank you, Gary.